Okay, it's time to start the class. I'm Dr. Bart Snapp. This is Math 1151. This is our second lecture. Today, we're going to talk a little bit about 1.3 and 1.4, just like we did last time. And we'll start, 2.1. What questions do you have before I begin? I'm not promising to answer any of them, but I'll do my best. Okay, last time, if I had to think, I'm going to try to recap on what I think might be the hardest problems from 1.3 and 1.4. Okay, that's what I like to talk about. And so here's one. This is something that I prepared for last time that we didn't get to. Okay, let's simplify. Simplify cotangent of tan inverse of 2x. Boy, this looks nasty, right? This looks like something out of a nightmare, sort of, right? Simplify this, okay. Does anybody have any can anybody answer in 2 words how you might want to solve this problem? What we're going to do in 2 words? Pythagorean theorem, yeah, we're going to use that. Draw a triangle. That's 3 words. Shoot, Bart. I said 2 words, and draw a triangle is. Oh, you said draw a triangle? Oh, that's good. You're better than me there. Draw a triangle. Draw a triangle. That's exactly what we're going to do. Okay. And so what we're going to do is we're going to assume that 2x is equal to tan theta. Okay. We're going to assume this, where 0 is less than or equal to theta is less than or equal to pi over 2. Okay. Assume 2x equals tan theta. So what we're going to do is we're going to draw a triangle forcing tan theta to be 2x. And it's going to be a right triangle. Here I go. Here's my right triangle. There's theta. And so what is tangent? Tangent is, oh, did I make a mistake there? No, it's okay. Tangent of theta is equal to opposite over adjacent, okay? And, we want it to equal 2x, right? Opposite over adjacent should equal 2x. And so what I'm going to do is I'm going to make this length 2x. Make this length 1. Is tangent of theta equal to 2x at this point? Check. Okay. What is the hypotenuse? How long is the hypotenuse here? Square root of 1 plus 2x squared, just like so. Okay. Excellent. Excellent, excellent, excellent. Okay, so now what do we do? Well, we want to compute cotangent of tan inverse of 2x. And what is tan inverse of 2x equal to? In short, like what's a Greek way of saying this? Theta. This is equal to theta. This equals theta. Look at that bright pink chalk. It's absolutely beautiful, okay? That's equal to theta. So this is equal to cotangent of theta. Aha. And so what is cotangent of theta? Cotangent of theta is equal to adjacent over opposite. Okay, and from the triangle, right, we can see cotangent of theta is equal to 1 over 2x. What do you guys think? What do you guys think about this problem? Is it super hard or what? No. Okay. If I explained it well, you should understand every step, okay? However, that doesn't mean that, yeah, go ahead. This assumption right here, you're not given this. All you're given in the problem, that's a great question. All you're given in the problem is this business here. Okay, that's the question. It's not that hard. You can kind of understand every step, but you guys got to practice this. And how do you study for a math class? Practice what? Problems. You work problems. You have to work problems. It's like an athletic event almost, okay? If you want to be good at shooting free throws, you got to shoot. How many free throws? Okay, I'm terrible at shooting free throws. How many would I have to shoot to get good? 1,000. Who said 1,000? 1,000. I have to shoot 1,000. How many math problems do you have to do? Answer, all of them. Okay? I would do all of them. I would try to do every one in the book. I would harass your TA about wanting more problems. I would go to my MATLAB. I would try to, oh, you guys know there's that special thing, like 9 to 5. I've sent you guys all emails. If you don't know what I'm talking about, for help with my MATLAB, okay? I'd go there. I'd try to work all those problems. I would sign up for the Mooculus. Remember I showed you this last time? Work all those problems. Just keep on working problems. Okay? That's how you get good at math. It's not about watching me and understanding what I'm saying. It's in you. I'm pointing like this so no fingers are pointing back at me. Okay. All right, so that was, I think this is a tough question. The next tough question that I think is, oh yeah, we were talking about inverse functions, okay? Inverse functions, and this has inverse functions all over it. The typical way, if you're given something, I'm looking for the eraser. If you're given a polynomial or something like this, the typical way to find the inverse function is to solve, okay? And so I'll do an easy example and then I'll do a harder example. Does that sound good? An easy example, then a harder example. Okay, so f of x equals x squared plus 3, okay? F of x equals x squared plus 3. A good thing to do anytime you're thinking about inverse functions is to plot your function. Okay? I'm going to plot my function. It looks like this. X squared plus 3 looks like x squared. X squared looks like this. Add 3. Boop. Boop. That's the sound you make when you plot functions. Okay, I'm not sure if you knew that. Okay, so now I want to find the inverse function of this. Now I'm going to have a little bit of trouble. Why am I going to have trouble? Does anybody know why I'm going to have trouble finding the inverse function? It's not 1-to-1. That's fantastic. It's not 1-to-1. Here I have two values, so I'm going to have to make a decision, and I'll decide to take the positive ones, okay? So now, how do I find this? Well, I'm going to show you how I like to do it, which may or may not be how you've seen it before. And as long as you do it right, I'm cool, okay? What I like to do is say y is equal to x squared plus 3. And then I solve for y. Solve for y. Solve for y. By the way, your answers get a lot better. What do you want me to do? Oh, yeah, exactly. See, solve for x. Thank you very much. Solve for x. Your answers get a lot better if you say what you're going to do before we do it. So we're going to solve for x here. Okay. So y minus 3 equals x squared, right? Ha-ha. Plus or minus the square root of y minus 3 equals x. I did it. Woohoo! Okay, so the problem is I have two values here. And an inverse function is often written, if this is f of x, my inverse function, I'm not done yet, is f inverse of x. And so now I just replace the y's with x's. And so this is equal to, and I'm going to make the decision, it's the positive one, x, square root of x minus 3. And what does that look like? Bart has to do a graphing calculation in his head. I believe, if I'm not mistaken, it looks like this. Okay? Yeah, what's up? You could. So this is a great question. She says, why not just write of y equals the square root of y minus 3? Boy, I love that. I think that's awesome. Okay? Because to me, variables are variables. I don't see any problem with that whatsoever. Okay? Because when you say this, you know what I'm saying? You are indicating that this is the thing you plug in. Now, because we always plot the x's on the horizontal axis and the y's on the vertical axis, it's going to be more clear. Whoever, yeah, go ahead.
I thought it was like f of the inverse of x equals
Oh, she's saying this. Put the y here. No. That's this is my preferred answer. Now I want to show you something, okay? And I think I'm going to answer your question. I think. If I don't answer your question, I don't really know what else to say, but I want to keep on moving. You can ask me after class or something, okay? But I'm sorry. But wait, what should f of f inverse be? Y or x? F of f inverse. It should be x. And so let's look at it. F of f inverse of x. We want to have the same variable. This is a fine answer, but this one might confuse the grader, and we really don't ever want to do that. Let's go ahead and evaluate this. So this is something squared plus 3. And what are we squaring? We're squaring x minus 3, right? So if I square the square root of x minus 3, I get x minus 3 plus 3, right? These cancel. And we get x out. X is the function that doesn't change anything, right? Does that kind of make sense? I can't tell. Okay. That's an easier example. Let's do a harder one. Here it comes. F of x equals 1 over x squared plus 1. By the way, what's the domain of this function? What's the domain of this function? This function here. What's the domain? The domain is all real numbers greater than or equal to 3. Taking the square root of 0 is fine. Square root of 0 is 0. Okay? We just don't take the square root of numbers. And look, you can see it from the picture. If you guys draw pictures, you can start to see, oh, the domain is all real numbers greater than 3. What's the range of this function? It's 0 to infinity. This thing goes off to infinity. Okay? All right, so now let's do this one. Okay, and what should I do now? I should say y equals 1 over x squared plus 1. And then what do? Solve for x. Solve for x. Whew, how do I solve for x here? What do I do? Yeah? Multiply both sides by the denominator. Excellent answer. X squared plus 1 times y equals 1. Fantastic. Now I can distribute. That's exactly what I'm looking for. X squared times y plus y. And I'm going to move over the 1. Minus 1 equals 0. Now what can I do? I can divide out by y, and I get x squared plus 1 minus 1 over y, right? And then we can say, now it will equal 0, right? And then we can go over here and we could say x squared equals 1 over y minus 1. You guys like that okay? Did I do it wrong? What, am I okay? take the square root. X squared equals plus or minus the square root of 1 over y minus 1. What? Oh, yep. Now, to be honest with you, I did this a slightly different way earlier. But this is fine. Okay, so now, and so what is our inverse function? What do we do here? Our inverse function is f inverse of x is equal to, I want to make one more condition. I'm sorry guys, I'm sorry. I want to make one more condition. I want to say that x is greater than 0. I want to say that x is greater than 0. So what was my big hint for the first one? I have a hint. Do you guys remember what the hint was for this one? We did it. What was my hint? It rhymes with graph it. Graph it, right? Graph it. So you may not know what this looks like, but I do. So that's okay. At least I think I do. Our function f of x here, this is f of x 1 over x squared plus 1. It looks like this. Okay? And so we're only considering it on this side, right? So f inverse of x is equal to what do I do? What do I put here? What do I want to have here? Do I want, if it's plus or minus, it's no longer a function, because functions can only, this condition for x being greater than 0? This is for the whole problem. That was my bad. My apologies. Okay? This is what's given to you as the statement of the question. So, if x is greater than 0 and x equals this, right? What do we want this to be here, plus or minus? Plus. It's got to be plus. I'm not going to write anything here. So that's correct. Okay? And what is the domain? What's the domain of this function? It should be 1 or greater. Is that right? 1 or greater. So 1 less than or equal to x. Is that good? Domain. And what's the range? Now remember, this gets flipped over. When you make inverses, you can geometrically think about what happens. It gets flipped over. And let's see how my geometric processing goes. I believe it looks like something like that, right? So what's the range of this thing? 0 to infinity. Range, it's 0. Are you guys cool with that notation? Yeah, what's up? Woo! Because, it's because domain, did I do this right? Should x be greater than 1 or should x be, let's see, what happens when x is less than 1? Did I actually flip this thing right? I don't know. Is this right? What do you guys think? Yeah? Yeah, so let's go ahead and plug it in here and see what happens. We don't need to look at the picture to figure this out. We can look right here. So when x is very small, okay, x is bigger than 1, right? Am I right? Because when x is small, wait, should x be bigger than 1? What happens when x is bigger than 1? It's negative. We don't want x to be bigger than 1. What do we want? We want 0 strictly less than x less than or equal to 1, right? Don't worry, guys. I mean, I know you must feel sorry for me making mistakes and then it's broadcast on YouTube for all eternity to see, but you guys all made it with me, so it's okay. I'm distributing. That's the type of guy I am. I just push everything on. No, I'm just kidding. Okay, so do you guys agree with this now? It's not about being right or wrong. It's about getting to the right answer at the end of the day. That's what it's about. Okay? Ooh, I shouldn't do that. That's just embarrassing. Okay, so now. Okay, so these were harder questions, okay? Anything you guys like to ask before we move on to... Yeah. Is the range the domain of the inverse? Is the range of the... wait. I'm getting scared by that, okay? And the reason I'm getting scared when you're telling me that, let's investigate something and see if rather than me just answer, let me just kind of draw a picture and see what we can think. What function, she asked, this is a great question by the way, okay? Is the domain of the inverse the range of the function? Is that what you asked? You can correct me if I'm wrong. What picture should I draw to help me understand this? I'll write the question on the board. Is the domain of the inverse the range, I think this is good, of the function? What function should I draw? What function has a funky inverse? What function am I dancing to right now? Sine. Sine has a funky inverse, right? Sine has super funky inverse, right? And what does the inverse of sine look like, right? So sine, I'm thinking about sine, okay? And we'll do sine, and then we can also do like x squared or square root or something like this. Sine, remember, sine looks like, ooh, that's kind of pointy for sine. Sine looks like that, right? But arc sine looks like it goes from minus pi over 2. Is pi over 2? Yeah, pi over 2 is greater than 1. So arc sine goes like that. Something like that, right? Okay, and so now, is the domain, well, the domain of arc sine is the range of the function. Okay, in this case, because the range of sine is minus 1 to 1, and the domain of arc sine is minus 1 to 1, okay? Now, what about, yeah, I think that's true. Yeah, looks good. I can't think of a counterexample right now, but everybody's staring at me and I get nervous. Okay, but it looks good. If somebody thinks of an example, let me know. Okay, but I think it's right. And you can draw pictures to help yourself out. Think about x squared too. What's the range of x squared? Did it work in our example? Oh, I erased it. Ooh. Okay. Did it work in our example over here? She's saying yes, and I believe her behind you. Yeah. You don't have to. I don't know. Okay, I'm making this up as I go along. Oh, shoot. Okay, so now, are we ready to do something else? Let's try it. Okay, so yeah, that looks good. We'll have to post, well, whatever. Okay, so now let's move on to 2.1. 2.1. Okay, so you know what I'm really looking forward to? Spring break. Let's try it real quick. Let's spring break, spring break. Come on, everybody. Spring, come on, why not? Spring break, spring break, spring. Now try this. Calculus, calculus, why not? Come on. Calculus. Okay, all right. So spring break. I want to go, you know where I want to go? I want to go to Myrtle Beach, South Carolina. Has anybody here ever been to Myrtle Beach? Yeah, what do you guys think? Ever go parasailing? That's fun, huh? Ooh. Okay, so Myrtle Beach, I'm not sure if you realize this, it's about 600 miles to Myrtle Beach, okay? This is in Myrtle Beach, MB. This is Columbus, okay? So now, suppose I drive down to Myrtle Beach, and it takes me 12 hours. It takes me 12 hours to get to Myrtle Beach, South Carolina from Columbus. It takes part 12 hours to get from here to Myrtle Beach. How fast did I drive? 50 miles per hour. 50 miles per hour. Okay, 50 miles per hour. Let's plot something. In calculus, you should always be plotting stuff, okay? If you ever don't know what to do, plot something. When in doubt, just start plotting stuff, okay? Sure, that's what I do. Now, let's plot this. So, we're plotting distance over time. If I'm driving at, and I have to make little notations. So 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, 6 hours, 7 hours, 8 hours. Oh geez, I'm running into 9 hours, 10 hours, and I still need more space. It's not a big deal. 11 hours, 12 hours, there's 12 hours, okay? And how far is it? It's 600 miles, so we're gonna go 100 miles, 200 miles, 300 miles. Oh gee, they did the same thing. 400 miles. Where are we going? 100 miles. Nobody answered. 600 miles. We're going to Myrtle Beach. Okay, and how long did it take us? Took us 12 hours to go 600 miles. That looks right about there. Is that right? I can't really tell. Looks about right. And if I drove at 50 miles per hour, my path looks like this. There we go. All right? Is that a realistic description of how you might drive to Myrtle Beach, South Carolina? She says no. How is it going to look in real life? Yeah, sometimes you go faster. Sometimes this would be like, I woke up in the morning, I started my car, I started moving, I ran, I jumped in the window and just floored it to 50. Not really flooring, but go to 50, and I just went straight from High Street all the way, And as soon as I get there, I just stop the car and fly out through the windshield, I guess. Okay, so, why did I say that? So, anyways, now, what it really might look like is something like this. You start off and you're going slow, then you're going a little faster, then you're going a little slower, then you're maybe going a lot faster, because here you got lost, okay? And you're going around and finally you get there, right? Does that make sense? Like here I got lost and started, I don't know, doing something, whatever, okay? So this is what it really looks like. So if I call this function, let me see, I have some good questions here. Okay. Call this function, if this is d of t, the pink function is d of t, distance with respect to time, right? What's d of 0? What should it be? Yeah, 0. And you know what? I should fix my d of t to make it look like there. That's a little better, okay? Makes sense? I'm getting close and I'm slowing down, okay? D of 0 should be 0. And D of 600 should also be, D of 600 should be 600, right? Wow, I'm crazy. D of 12 equals 600. Is that good now? Whew. Okay. What's D of 3 equal to? What's D of 3 equal to? Can anybody tell what D of 3 equals? Yeah, let's see. It looks like maybe 180 miles. Does that look about right? Okay. So D of 3 is about 280. 180, thank you. Not to be confused with 280. Okay. Common confusion, so I'm told. Let's see. What's D of 5? That's close enough. It's going to be about 250 maybe. Is that okay with anybody? D of 5 is equal to 250. If your picture doesn't look like mine, just change all the numbers. Okay? D of 5. And then what's D of, okay. And that looks good. Okay. What if you wanted to know how fast you were going at hour 5? Is the answer 50 miles per hour correct? Were you going faster or slower than 50 miles per hour at hour 5? Yeah, I'm on the curve here. How do you know how fast I was going? I'm right on the blue line, so you say it should be the same, right? Okay. Let me ask you another question. These are good thoughts. I like these thoughts. Aha, it's increasing. The slope is much steeper, right? And if you're going faster, this is 50 miles per hour. What would going 60 miles per hour look like? A steeper slope, right? And going 30 miles per hour would be a less steep slope. Does that make sense? So was I going faster or slower at hour 5? Faster. And it might turn out that when we try to estimate how, it might be like unrealistically fast, because I'm not sure if you noticed, I just kind of did this. But we'll just see what happens, okay? And maybe we can make up a story problem about it. Maybe I was driving the Batmobile. Ooh, this to infinity is off. Okay, so now, how fast was I going at 5 hours? How would we find that out? What should we do? Okay. Yeah. How are we going to take the derivative of this thing? You don't have a formula. That's good. That's a great idea. Okay, that's a great idea. How can you tell me what to do? Yeah, I don't know what the formula is. I just drew that thing. You know. Yeah? Yeah, I could do the tangent. Okay. How can I find out? What's the formula for slope? Does anybody remember that? Rise over run. Do I have a picture here? Can I compute rise over run for some run? I think I can, right? So let's go ahead and try to do that. Let's see, 5 hours. Now, what could we do? First thing, you know what we could do? We could look into the future a little bit. We could say, okay, so what we could say is d of 5, and I'm going to write this 5 plus 1. What's 5 plus 1? 6. I know. Why am I writing 5 plus 1? Why don't I just write 6? Because I'm imagining going over this far, okay? I'm making a little window around this. Am I making any sense? And I'm going to compute rise over run. That's what I'm going to compute. So it's going to be d of 5 plus 1. And then I'm going to subtract d of 5. And then, how much time went by? 1 hour. Oh, that's an easy fraction, right? Okay, and let's hope that not too much stuff happened, or else. Okay, so what is d of 5? Might be in the Batmobile here, guys. I don't know. What is d of 5? 250. Okay, and what is d of 6? Looks like it's about 300. Okay, so this is equal to 50, right? But what do you think? Am I going faster? Why is it equal to 50? What happened here? I know I'm just estimating, but can somebody, yeah. I used too large of a section, right? I'm computing velocity. Remember, this is basic like 6th grade or 5th grade stuff. D equals distance equals velocity times time, sine distance, I guess. Okay? And so look, we're just doing distance. We're really just doing distance over time. That is the slope formula. That is the change in y over the change in x. They are the same. And that's just what we did there, right? Okay, so let's do a smaller window. Right? What's a smaller window we could pick? A half hour. So we could divide by 0.5 here, okay? So now, at top I'm going to write d of 5 plus 0.5 minus d of 5. This is just change in y over change in x. This is just how far you've gone in this amount of time. It's just distance over time, right, to find your velocity. All the same thing. Okay, well, what's the answer look like it is? So what is, here, this looks like it right here. So this looks like it's maybe, so d of 5 point, d of, is it 5.5? 5.5. And that looks like it's about 290. Is that acceptable? 290. And what is, okay, so what's 290? What's d of 5 again? 250. What's 90 minus 50? 40. And we divide by 0.5? 80. Aha. So that aligns much more with what we think, how fast we were going, right, at hour 5, maybe 80 miles per hour. Okay? All right, great. How would we make it even more accurate if we wanted to? Shrink this down. We want to make this little window as small as possible. Can we make the window size 0? No, why not? If we divide by 0, the board bursts into flames, the foundations of mathematics come crumbling down upon our heads. Everything's terrible. Okay, we can't divide by 0, it's undefined. But we can divide by small numbers. Okay, this is getting at the idea of what a limit is. We want to put smaller and smaller numbers in there, right? It's how, does anybody here have a GPS? Your GPS knows how fast you're going, doesn't it? Does your GPS attach to your speedometer? No. This is how your GPS works. It marks where you are at a certain time, a very small interval, and then sees where you are a very small amount of time later, and then it does exactly this calculation. Okay? That's how it works. That's how it has to work. Okay. That's great. So, what we're really computing here to get what we might call the instantaneous velocity. I have to erase my picture here of the United States. What we'd really be doing is we'd be taking the limit. This is as h goes to 0. Maybe h stands for hours. Maybe. Of this, of d, and then I did 5 plus h minus d of 5, right? And this is the idea of taking this window and making it smaller and smaller. We're not plugging in 0 exactly, but we're taking the window and we're making it smaller and smaller. Does that make any sense? I can't tell. I have no idea. Okay. Now, of course, this would be the instantaneous. Oh, geez, instantaneous. I'm scared. EOUS velocity. No, VE. Okay, the instantaneous velocity. Okay, and of course your speedometer. Is anything there right? Okay, good. Good enough. 1 out of 2. Okay, passing. So, your speedometer computes instantaneous velocity. Your speedometer calculates this limit. That's pretty cool. Okay. Now it's time. Hey, what questions do you guys have about this? Of course, this was all done by just looking at the picture. That's how I did it. I had no functions around. Yeah. He says, hey, if you want to know how fast you're going, shouldn't you look at a half hour before 5 as well, right? That's what you're saying? Yeah, that's a great point. And when we write this, we're really taking our hours to a window of 0 from both sides, from a half hour before and a half hour after. Just for time constraints, and because this calculation gets boring after a while, I only did it from the one direction, okay? But yeah, you really are going little windows on half hour before and half hour after, okay? What other questions do you have? I made up this question. You know, the point of the question was to kind of discuss it, to look at the picture, to think about what's going on, to think about what we're doing here is we're really taking smaller and smaller time intervals. I didn't really realize that that's how the GPS works until I was standing right here, but that is how the GPS works, okay? It's also how, ever been driving along and see like this highway is monitored by air? You guys ever see that? That's how that works too. They have two little white lines on the road. And if you drove over the one, they time you from driving over the other. And then the aircraft can figure out how fast you're going. Okay. All right. So, got to get an eraser. I have two examples I want to show you. Oh, maybe 3. 2 or 3. Maybe 4. I don't know. Okay, so here's 3 examples. Slowly moving more abstract. I have f of x is equal to x squared plus 10x plus 25 all over x plus 5. That's one example. And I want to compare that to g of x equals x squared plus 10x plus 25 all over x minus 5. And I want to compare that, both of these, to h of x, which is equal to x squared minus 10x plus 25 all over x minus 5. And the question I'm going to ask is what happens to these functions at x equals 5. X equals 5, question mark. What happens when x equals 5? And what do I like to do whenever I'm starting a problem? I like to graph it. I think that's fantastic. So fantastic. We all have graphing calculators. If you don't have a graphing calculator, you can go to you can go online. You can Google Geogebra, and it will plot things for you. If you can't figure it out, I'll send you instructions or something like that. It's super cool. Okay. So Geogebra. It's like algebra and geometry put together in a fusion. Okay. So now we're going to plot this. This is x. This is y. What does this look like? Can anybody tell me what this looks like? As x goes to 5? What'd you say? Minus what? Yeah, what does this look like? Does anybody know what this looks like? We're saying x equals 5. Y equals x? Yeah, it does look a lot like y equals x. And how'd you get that? Yeah, this is equal. This is. He said, "Oh, that's a good idea." But you know, you can factor the numerator here. The numerator is x plus 5 times x plus 5, and if I divide by x plus 5, what happens? What do I get? I just get x plus 5. So this looks like x plus 5, which looks a lot like y equals x. So y equals x plus 5. And so it's going to look something like this. Does that make sense? And I can keep on going the other way if I want to too. Let's not go too far. All I care about is the positive stuff, okay? So that's what this looks like. How about g of x? What's g of x look like? Does it look the same or different? It looks different. It looks very different, okay? G of x has problems. You can't do it because the denominator equals 0. X minus 5, you plug in 5, everything, bad stuff happens, right? So here we go, 5, we have, here I'll use hot pink for the asymptote. There we go. Looks like that. All right, and then let's see, orange for the function. And then it looks like this. Okay? Makes sense? That's what it looks like. And what about our last example? In our last example, we still have this sort of x minus 5 business going on, right? This is the good case. This is the bad case. This is the strange case. Okay, so here we go. X, y. All right. So now, put 5 here. What's this look like? What is f of 5, by the way? F of 5 is undefined. If I plug in 5 here, I have to divide by 5 minus 5. That's dividing by, it's f of 5. Oh, sorry, we're talking about h. H, people. Bart. H of 5 is undefined. H of 5 is undefined. Exclamation point, underlined. Okay? Can't plug it in. But what can we do? What's it going to look like if we plot it? Yeah, who said that? Yeah, what's going to happen? Can you tell me a little bit more? He says it's going to look like this one, but there's going to be a hole. And can you tell me how to get there? If not, that's okay. But if so, that's fit. He doesn't remember. That's okay. Is anybody? Yeah. She says, take the top and let's factor it. Okay, and we can factor this. This is equal to x minus 5 times x plus 5, right? All over x minus 5. Yeah, thank you very much. Yeah, see? Thank you. Correcting all my mistakes. Next time I'm going to give a lecture where everything I say is wrong and you guys have to fix every single step. It'll be just like every day. So now. Oh yeah. So now what we should do is we should declare x is not equal to 5. I am demanding x is not equal to 5. And if x is not equal to 5, what can you do? It rhymes with remide. Okay, it rhymes with, yeah. What? Divide. If x is not equal to 5, we can divide. Okay, we can divide if x is not equal to 5. And so, boom, I divided, right? I divide. And now what? What's it look like? It doesn't look the same because it looks like x minus 5. Okay, so I need to change my picture here. Okay, there we go. But it's still it's going to look like this. And then what's going to happen? X minus 5, it's going to go up here like this. And then you're going to have a circle, an empty hole here. Okay, there we go. That's what it looks like. A tale of 3 functions. Okay, so we have this. So now, we've been trying to introduce the idea, 2.1 is about the idea of limits, okay? And one very early way to start is you just kind of follow the function along and see what it should be, okay? And my phone is telling me it's 2:40, which means I'll stop in just a second. Okay? So what is the limit as x goes to 5 of f of x? What's the limit as x goes to 5 of f of x? Can you guys tell me this? Here's f of x here, right? I can just plug it in. It's fine. The limit's like you're traveling. It's like you're driving along and see where you go. So this is equal to 10. What is the limit as x goes to 5 of g of x? What happens as x goes to 5 here? I'm trying, and then, yeah, positive, negative. That's a good guess. But the thing that I want to see is does not exist. Okay. Does not exist, okay? Here, it's like you have railroad tracks, and if you remember the old Superman with Christopher Reeve, at some point he lies down on the railroad tracks and the train just goes over him, bump, 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 and the train's going along, and it's fine, okay? And so the limit here, so the limit as x goes to 5 of h of x is equal to 0, okay? Because even though the function's not defined here, if you're going, you can get arbitrarily close. That's the idea. We're going to talk about this more on Friday, okay? Think about this. Have a nice day. This is x plus 5. And then I evaluated it. It's like I'm moving all the way over to 5, and there should be 10.
Question.
Yeah.
So earlier when you were talking about that lady asked a question about whether or not the domain.
Yeah.
So that's only that one is always true, but the opposite.
The opposite's probably not.
Is yeah. So that only exists if it's a one-to-one function, right?
Yeah.